Hello and welcome back to neural networks. Today we are going to discuss a very interesting property of neural networks, and what that essentially, I'm going to talk in detail about what the property is, but what the implication of that property is that neural networks with a single hidden layer. So if you have a neural network, a multilayer transform with a single hidden layer, then it can, in theory, approximate any function to an arbitrary level of accuracy. So let's say you've got a function, let's make a function of a single variable. Let's say you've got a variable x, this is the independent variable, and then you have got a dependent variable or a function that is h of x, and let's say you've got a function like this. Now what this theorem states, we're not going to do the proof, but we're going to understand its implications. What this essentially says is that you can make a neural network that can approximate this function. Let's say like this, it can develop an approximation of the original function. So we can develop an approximation from a neural network, h dash of x, that is able to approximate this function to an arbitrary level of accuracy. So let's say if our approximation that we can call g of x is, we can have arbitrary level of accuracy. And this neural network representation of a given function just needs to have a single layer. Now, if you think about it, what we've been doing in various types of transformations, for example, even PCA or Fourier transform, if you know about that, or other types of wavelet transforms, is that we can write a complex function or an approximation to that complex function in the form of simpler or basis functions. So, for example, the Fourier transform, what it does is that it expresses a very complex function, a square wave, for example, as a summation or a weighted summation of basis functions such as sines and cosines, right? Similarly, what we're saying here is that if we have a neural network, and this is a picture of a neural network, right? So we have these neurons, and if we have a single hidden layer of these neurons such that each neuron takes a weighted summation of the inputs. In this case, we only had a single input, or it was a single variable function, but we can have multivariable functions as well. So we can have, let's say, two-dimensional inputs. We can have d-dimensional input in general, and each of these input feeds into each of these neurons. And what that neuron does is that it does a weighted summation of that input for a given input, right? And then it applies an activation function or a basis function on top of that. And then what happens is that output for each of these hidden layer neuron is fed into this neuron, right, at the output layer. And we get output of this neural network, right? And what this theorem says is that this structure can approximate any given function to an arbitrary level of accuracy. And that's huge. First, it allows us to express a given function in the form of on the basis of our activation function. So we have our inputs, we have our activation functions, and then we can express the output of that function, or we can approximate the output of that function as simply a weighted summation of the output of these activation functions, much like what we have in the Fourier transform, if you're familiar with that, right? So all we are saying here is that any function can be expressed like this. And the funny thing about this, or an interesting fact about this whole formulation or the universal approximation property of neural networks, is that this was known even before neural networks came into existence. There were people, mathematicians, who figured out that if you have any function, then it can be approximated by this structure that we have over here. And coincidentally, this structure, that is, we have an input that is being multiplied, each of the inputs gets weighted, and an activation function is applied on top of that, or a basis function is applied on top of that, and then we have the summation of those activation functions. This can approximate any function to an arbitrary level of accuracy, right? And coincidentally, this structure coincides with the structure of a neural network with a single hidden layer. So as long as those mathematicians figured that as long as f, or your activation function, is a non-constant, so it doesn't have to be constant, it has to be bounded, and it has to be monotonically increasing continuous basis function or an activation function. That's what we are calling it. As long as it satisfies those properties, then we can approximate any function for a given input with a combination of these p factors or p basis functions. And this is what a neural network is, right? So we haven't done a proof of this, but this was proven actually before the emergence of neural networks. And what people observed is that a neural network is nothing more than an implementation of the same structure, right? So neural networks have this interesting property that they are able to approximate any given function. And the way they do it is that we know what the function looks like. For a given input, we know the output, right? So we apply the given input, we compute for a given value of weights, the output, and then we try to optimize or try to tune these weights, these ones and these ones, so that the output of the neural network matches the function that we have to an arbitrary level of accuracy. So we do an optimization problem, so where we try to minimize this with respect to the parameters of this neural network, which are W's and V's. So if we can do that, if we can achieve this optimization, then that means we have learned this function, right? So we can express this, and all we need to do is to identify what these values of weights and biases are, right? And we are going to take a look at a code that allows us to write any function, and you can play with it as a summation of these basis functions. Okay, so we're going to take a look at the code now. So what this code actually does, before we start looking at the code, is we have a function, let's say g of x is equal to sine 4x plus cos 5x or whatever. It's a function of a single variable, and what we are going to try to do is to approximate this particular function by a neural network. And we are going to use a neural network with sigmoid activations. And just to give you a brief reminder of what a sigmoid actually looks like, it's a function that can look like an S or an inverted S, some people call it, shape like this. Okay, so we are going to use these as the basis functions, and then we are going to try to express this function that is over here as a weighted summation of these functions at the output for this given input x. Okay, so the output of a single neuron depends on its net input, which is weighted, or the summation is the summation of its inputs with bias. The output is the sum of the outputs of all hidden neurons. All we want to do in this process, or what the code is going to do, is that it's going to find those weights, it sum up to produce the target function. Okay, we already have a solution over here, but if you look at all of these functions, these are sigmoidal functions. It's really hard to imagine that when we sum up all of these, this actually leads to this thing, right? So that's what we are going to find out. So this is the code. We are going to use PyTorch to implement or approximate our function, or develop a neural network that will be able to approximate this function. So first we define the function. It's sine of 4x plus cos 5x, and then what we do is we first of all go ahead and plot this function to see what it looks like, and then we simply convert these variables x and y. So x is the input, which goes from -1 to +1, and y is the corresponding output of this function that we are interested in approximating. So what we do next is we first of all see that if you use all of these sigmoids, then we can approximate this function as a summation of all of these functions, and that's what we are going to do. Okay, so all this does is it plots all of the different type of sigmoid functions, and then we can try to develop an approximator. So the first hidden layer has a total of p neurons in it, and we specify the number of neurons we can use. We can specify p is equal to 1 and p is equal to 2 and so on. And what this allows us to do is we first of all make a hidden layer matrix over here, which has p neurons in it, and each of those neurons is going to take input from all the input dimensions. In this case, it's a single variable function. So your D input is 1 and your D output is 1. The number of examples we already have that number in place. And we are going to approximate all of these weights. And once what happens, the first step that happens is we take the dot product of these weights with your given input, and then we add a bias term. So this is each of the neurons in the hidden layer. What it does is that it takes the input, multiplies it with a corresponding weight, and then we apply a sigmoid on top of that to produce an output. So this is going to be, for a given input, this is going to be a vector of the outputs of all hidden layer neurons, and then what we do is we multiply it with the output layer weights to return an approximate value of G. And what we are interested in is finding what these WB and VB are going to be. Okay, so we do that using stochastic gradient descent. We use an optimizer. What we do is we do multiple epochs. We take all the inputs. So in this case, we're using 3000 epochs. You can change that number. We take all the inputs. Remember, X is the input over here. We take that as input. We pass it through the approximator, which is this function over here, which implements a single hidden layer neural network. And then we approximate that. We get the output. We compute the difference between the output and the target as a loss function, or we call that as an error. And then we do simple back propagation over it, or we can or optimization over it. So this is the representation component, this is the evaluation component, and then this is the optimization component. And once we do that, we can see what each of the individual basis function looks like and what does the summation of all of those look like. And as you can see in this case, we get very good convergence. So this is the convergence plot. Over epochs, or log value of the loss goes negative at about 30,000 epochs, and you get a pretty good approximation. But what it essentially means is that for a given input, each of those neurons produces a small or contributes a small factor to this overall approximation. And if you sum up all the contributions from all the neurons or their outputs, you get this function. So that's how you can go ahead and play with universal approximation and understand this very important property of neural networks. So let's play with this code. If you use a single hidden layer, a single neuron in the hidden layer, so the network architecture you have essentially translates to a structure like this. Let me draw it for you. Oops, sorry. Let's go back. I can't seem to get my pen, so apologies for that. Let's say we've got a single input, X, that feeds into a single neuron, which then goes ahead and generates the output. So you've got this input, there is a single neuron in the hidden layer, and then there is a neuron in this output. So if you have a single hidden neuron, that's what's going on. This neuron is going to also have a bias term. So it has a corresponding input, which is always 1, and this is the bias term. This is the weight, and then this is V, and then this one also has a bias, and I'm going to call it, let's say, U, and then we have an output, Y. So if you write the mathematical formulation for this simple neural network, what it means is we have Y is equal to an activation function applied on the input to this net input of this neuron, which essentially means V multiplied by whatever this neuron was producing, and we're going to write an expression for that, plus U. Okay, and then let's try to write what this neuron is producing. It's producing an output, which is an activation function applied on the weighted input, which is Wx, okay, this weight and this X, and plus B. So you can write this as this neural network with a single hidden layer in the form of this. And all we are trying to do is we are trying to minimize the loss between this output and the corresponding target value that we have for the given function. So we are doing that by trying to find these optimal values of W, B, U, and V. So that's what that optimization process is going to do. Okay, so we have these, if you use a single neuron, this is the corresponding structure. And as you can see, it's not a very good approximation. It is an approximation because we had a single neuron. So this is the approximation that we get, and it resembles a sigmoid. But as you can see, it's not a very good approximation, right? Let's see what happens once we increase the number of neurons in the hidden layer. So let's use 2 neurons. And if you use 2 neurons, then the corresponding neural network structure simply becomes, we have a single input, we have that input going to these 2 neurons, and their output is then going into a single neuron at the output, which generates our final output from our approximation from our approximator. And as you can see, these 2 neurons can have, so for example, this one and this one, they have, one of them produces a very sigmoidal output, the other one is producing a different output. But once you sum these together and add it to the output of the third one, or the bias term, we get a pretty good approximation. So just changing from 1 to 2 actually has enabled us to approximate this pretty well. And this approximation is going to improve as we increase the number of neurons in our hidden layer. Okay, so if you have 3 neurons, you can see it's a much better approximator. And then if you use 6 neurons, you have all of these functions which are being added up, and you get a pretty good approximation, right? So I hope now you understand by this time that we are able to approximate any arbitrary given function to an arbitrary level of accuracy using a neural network with a single hidden layer. And I welcome you to try it out for different types of neurons, different neural architectures, different activation functions, but more importantly, different type of functions that we are trying to approximate. So play with it and try to get a hang of it, how this universal approximation works. Now, it sounds really cool that we'd be able to approximate any function in the universe. So universal approximation is a pretty big word to use, but that doesn't necessarily solve all of our problems in the universe. So the universal approximation theorem means that regardless of what the functions we are trying to learn, we know that a large multi-layer perceptron will be able to represent this function. However, we are not guaranteed that the training algorithm will be able to learn that function. First of all, if your number of neurons required to approximate a given function is pretty large, you have a very large number of neurons, you have a very large number of parameters, and your optimization can fail. And then even if you learn that particular function for which you are given input, variations of that functions, the neural network may not be able to approximate or learn to generalize, and that is a big problem. So learning is different from optimization. All this theorem says is that we'll be able to learn training data with an arbitrary level of accuracy for a given problem. But as we know, being a data scientist, is that our goal is not simply to learn what's there in the training data. The goal is to generalize to unseen examples. And representability, just being able to write a function as a single hidden layer function, does not guarantee learning. So representation is a representability and optimization are necessary conditions for learning, but they are not sufficient conditions. Okay, so that's really important to understand. And this is why, even though these neural networks can have very large, they can have a very good ability to approximate any function, they may still not be able to generalize. Okay, and adding more and more neurons to your approximator, as you can see, gives you a better approximator, right? But for that particular training data set, there is no guarantee that you'll be able to approximate better on or able to generalize to novel examples. Okay, and that is the trade-off between optimization or memorization and generalization. So what we want is a neural network that uses this training data, learns the representation of the training data, but also is able to generalize to unseen training examples. Okay. Another way of visually thinking about universal approximation is, let's say, what we've done earlier. Let's say I ask you to take a piece of paper and I ask you to approximate different shapes using straight cuts again. So let's say if I ask you to approximate, for example, a square, all you need is 4 square cuts, right? And you'll be able to approximate that. If I ask you to approximate a pentagon, for example, all you need is and the functions that are given to you are straight lines, or what you're going to need is 5 cuts, right? So you can think of these neural networks or these functions within the universal approximation representation of a neural network as making these straight cuts. As a matter of fact, if you use rectified linear activation function, which doesn't exactly satisfy all the conditions we set out for a basis function, but let's not get into that at this point. You can think of it as making these piecewise linear cuts, and it's a piecewise linear approximation of a given function. So if you have these 6, if you want to approximate a hexagon, you're going to need more cuts. And if you have a circle that you're trying to approximate, you're going to need a very large number of straight cuts to get to a certain level of arbitrary or an arbitrary level of accuracy. Now, the problem with universal approximation is a neural network with one hidden layer can be used to approximate any shape. So we should be able to, as we increase the number of neurons in the hidden layer, we should be able to approximate any function or any shape. However, the approximation might require exponentially many neurons. So going from an approximation of a hexagon to a circle, the number of neurons that you're going to need is going to go up exponentially, and that is a problem. I really like this example. It's taken from this paper, and I welcome you to read this if you're interested in this particular property. But what it essentially says is that we need, in order to have good approximations, the number of neurons can increase exponentially. And that leads to a very large energy footprint or a very large computational complexity. So we may have a neural network that may be able to approximate everything, but the number of neurons required to approximate any function can be quite large. So if you think of a single hidden layer neural network, then if the data dimensionality of that neural network is D, then each input example is D-dimensional, and then each of those neurons, there are P neurons in the hidden layer, the number of trainable parameters, or number of weights that we want to learn is essentially PD plus P plus P. And I welcome you to try out why this is the case, but this is a number of parameters, and if this grows to, or we need a very large number of functions or a very large number of parameters, your optimization can fail as well. So we can approximate any shape that is given to us, but it may not be easy. Okay, so that is the fundamental problem with. There's a visual representation of this fundamental problem in universal approximation.